Welcome to Physical Attacks and Countermeasures, the 10th session. We learn a lot of things about different sergeant analysis attacks, particularly our focus was on power analysis, which is similar to EM analysis. I mean, instead of measuring the power, you can measure the electromagnetic radiation of the chip and perform the same attacks that you have learned. Now we move toward countermeasures and the schemes which are known up to now to counteract these kind of attacks, how to protect the implementations against these kind of attacks. And today we focus on hiding because there are two categories of countermeasures, and our focus will be on hiding. There are not much to say about hiding compared to masking, which is another type of or another category of the countermeasures. In masking, there are many more papers, there are many more discussions on the topics to deal with, and we spent also 2 sessions on masking, which is still short. If you want to cover everything which is done at the moment in that area, we probably need the entire course about masking. Now, the agenda, not only for today, generally about the countermeasures. One category is hiding. In the hiding countermeasures, we have 2 categories, randomization. They are just some words, and I will explain the concept later. There are some techniques to add noise to the implementation by dummy instructions, by clock randomizations, and also shuffling. We will see them. And also power equalization, which is also another category of hiding. They try to filter the signal that you measure. When you measure the power consumption traces, you learn how to measure it. There are some techniques to filter this signal inside the chip, and also some other hiding techniques which are also equalization or power equalization, that they are called dual rail circuits and also random precharging. And another category which we do not consider this session, we will work on it, or we will deal with it in the next 2 sessions, is about masking. We will see Boolean secret sharing schemes, which is also called Boolean masking, and also multiplicative secret sharing and combination or conversion between Boolean and multiplicative masking, and some hardware masking, some topics which is related to apply masking in the hardware implementation, which is called also threshold implementation. And that's all, with respect to masking and hiding schemes. Now, as I said, today we focus on hiding. And what is the purpose and the goal of hiding is actually to reduce the SNR. This is what you already learned. The SNR in the context of sergeant analysis attacks is defined as variance of the signal by the variance of the noise. And you also learned how to calculate this for every implementation, and also based on every target that you have. The signal that you want to exploit. This is what you already learned. And the idea of hiding countermeasures is to decrease this SNR to make the attacks harder. And this can be done by decreasing the variance of the signal or increasing the variance of the noise, right? What you should consider and you should keep in mind, hiding countermeasures are not able to prove something which is secure. It means that they make only the attacks harder. How much they make the attack harder? You may not be able to give a threshold or something. They just reduce the SNR. In one implementation with particular setup, the attacks might be not possible. But if you change the setup, the measurement setup and the facility that you have, or use some sophisticated signal processing schemes, you may overcome this hiding countermeasure, again perform the attack. There is no guarantee on the security of implementation if you have only hiding schemes or hiding technique in your implementation, which is different to masking. What we learn later in masking schemes, you can define the adversary model, and under this adversary model, you can prove the security of your implementation. Good. Now, the schemes and techniques that we see today, they are all based on increasing the variance of the noise or decreasing the variance of the signal. Randomization techniques, they try to randomize the power consumption by constantly changing the execution order, because what you have learned in the SPA, for example, the execution order is important. Yeah, it means that if you are able to find out what is the path which is performed, then you might be able to recover the key. And also in the DPA or CPA or these kind of attacks, what you have learned is that everything should be aligned, right? The power consumption traces at every clock cycle, they should be aligned together. And then if you make them misaligned, then you add some kind of temporal noise into your power consumption traces. Yeah, then the randomization can be done in two domains. At the amplitude domain, yeah, for example, there is another module inside the circuit, yeah, which consumes as power with some random data, which are not considered in your attack, which are completely irrelevant to the target that you want to find out. For example, you have an AES, and at the same time there is another AES which works at the same time inside your module or inside your circuit, and it also consumes energy, but with completely random input and random key. Now you don't know the input, you don't know the key of that extra module, and it consumes energy and it makes noise into your measurements. As I said, they increases the noise. Yeah, by increasing the noise, you have increased actually the denominator of this SNR, of this fraction. And then equalization techniques try to achieve an equal power consumption for every instruction or every operation at every moment in time. Means that the power consumption of the system should be completely irrelevant and not dependent on the process which is performed by the device. Means that doesn't matter which operation is performed, which data is processed, always the same amount of energy should be consumed. Means that if you have a microprocessor, it doesn't matter if you run the AND operation or XOR operation, then the power consumption should be the same pattern of the power consumption, and also the data operands of these operations should not have any effect of the amount of power consumption. And these equalization techniques is clear. They try to decrease the signal, which means that decreasing the numerator of this fraction. And then at the end, you will have a smaller SNR. Of course, you can combine them. You can have randomization technique to increase the variance of the noise, and at the same time, equalization techniques to decrease the variance of the signal to highly decrease the SNR. I mean, they don't have any overlap with each other. Yeah, you can use any of them or both of them. Let's look at the randomization schemes that we know. As I said, they can be done in the time domain and also amplitude domain. Again, I explained that you can randomize the amount of power consumption by generating noise. As I said, this is the amplitude domain, yeah, by consuming some energy at the same time when your device works. And also you can increase the noise, or you can run the implementation at different time instances. We will see some examples probably in the next slides. But what is important, I think I explained this a couple of times, that the power traces should be actually aligned. Yeah, this is what you have learned. Yeah, you have some power traces, different clock cycles. If the power traces are something like this, that they are not aligned, the next power trace actually is something like this. Yeah, and so on. Then if you run the attack or DPA or CPA on this, then this peak, yeah, this peak actually doesn't happen at the same time. You know, they are not well aligned together. Of course, if you run the attack just like this, then you need many more traces to perform the attack, because this just makes the attacks harder. You know? I mean, they do not prevent the attack. Because anyway, if you increase the number of traces, there will be some traces that they actually have exact at the same point in time, the peak, yeah, and then it will be aligned. Then the solution for that is to detect the peaks for every trace, and then make a, for example, window over this, for example, 50 points before and 50 points after, and the same for each of them. and then extract another trace, means that you turn this to another trace which has just 100 points, and then 100 points, and then 100 points, and then 100 points. And then you do this for every trace individually, means that another trace, that you make here another trace which is well aligned. And this one is also well aligned based on the peaks. Clock cycles mean that they are well aligned. And so on, and then you perform the attack on these traces, yeah, not on the misaligned traces. Yeah, then you need some pre-processing steps. Of course, if you increase the clock frequency, then probably this misalignment doesn't have that much effect, yeah, because the power consumption traces anyway will be overlapping on each other every clock cycle, and then this misalignment doesn't have a strong effect, and you don't see the peaks to be able to align them again, because anyway they are overlapping on each other, and you probably can perform the attack easily. This is what I already explained. Yeah, the denominator of the SNR is increased and the SNR will be decreased. And how to do this? Yeah, how to do the randomization. One option that you have, particularly in CPUs or software implementation, is dummy instructions or dummy operations. It means that you randomly insert some dummy operations in the implementation. But of course, these dummy operations should be randomly selected every time that you run the AES, for example. It should not be constant. Of course, you add some dummy operations, but if they are constant and they are always the same, then it doesn't have any effect on your attack. They just make the power consumption traces longer. Then one option is to have the interrupt, for example. Yeah, there is an interrupt, but it should be very frequent, and it goes into the interrupt routine, and then again it waits there for a couple of clock cycles, which is also randomly selected, that how many clock cycles it waits there. This is very simple, and it can be done particularly in software. Sometimes it's also said that it's better to insert the same amount of dummy operations, but at different positions. Yeah, means that you do it in a way that anyway the length of the power consumption traces stay the same. Or let's say the number of clock cycles that the implementation needs to perform the operation is also constant. This has some advantages, and also sometimes it doesn't have any advantage at all. But you may try to do it, but if you don't do it, actually it doesn't harm, and the attacks will not be harder or easier. Another thing that you can easily do, or more easily do, with less overhead, because the dummy operations will add the number of clock cycles that you have. Yeah, but another option is shuffling. What is shuffling? Shuffling means randomly change the sequence of operations that they do not have any priority on each other. For example, AES. What are the operations of the AES? Let's write the operations of the AES round by round. You have an add round key, and then sub bytes, and then shift rows, mix column, and again add round key, and again sub bytes, shift rows, and so on. First of all, if you have a software implementation, how do you write this add round key and sub bytes together? You write a loop for I equals, for example, 0 till 15, and you say, suppose that S is P, plain text, and you say SI, just 1 byte, is the S box of plain text I XOR KI. This is what you usually write, simply in software or pseudocode, it doesn't matter. Then who said this order should be from 0 to 15? They're completely independent of each other. Then you can randomize that order. What you can do, you can say, then I write it as this for I equals the same way, 0 till 15, and you say S of R I is the box of plain text of Ri x or k Ri. And then what you need to do, of course, this S equals P stays there. Then what should be R? R is you just permute zero till 15. You know, there are just indices from 0 to 15. In a vector, you just permute them randomly. Of course, there are some ways to do that. Yeah, I mean, for example, you write the vector as R at the first. It has 0 and then 1 and then 14 and 15. And then what you can do, you can select two of these positions and then swap them. For example, randomly select this, and then you swap them. And then again, you randomly select two other positions and then swap them. Then how many times you have to do it? There are some studies about this. Yeah, I mean, then you select a number, for example, 15 times, then or 16 times. Then you do this, swapping the positions randomly, and then of course it doesn't have the full entropy, because the full entropy will be all possible ways to have this vector from 0 to 15, which is how many times? What is the maximum number of the way that you can write 0 to 15? 16 factorial. But of course, this is the full entropy, the maximum, but you usually, by swapping the positions, you don't get the full entropy. But of course, depending on how many times you swap two values or two positions, then you can increase the entropy. This is one way to randomize this. Then what happens in the power traces? In the power traces, then suppose that there is no clock jitter. What you have seen, what I have shown, that they are misaligned, there was clock jitter. There is no clock jitter here. And then sometimes here a box or a state 1 is processed, and a state 3, and then a state 2, and then a state 10, S15, and so on. The next trace that you measure, this is very well fully aligned, but it will be S2, for example, S10, S3, S15, S11, and so on. Then when you perform the attack, at this point in time, everything is well aligned. But for example, you target the first S box. You target K0. But then it doesn't happen necessarily here, because S0 sometimes is processed here, sometimes here, sometimes here, sometimes here, and so on. In different places, different clock cycles. Then if you have the full entropy, then 1/16 cases, S0 is processed there. Then, for example, here is. Then here is S0, and S0 is processed there, but not always. Because there is another clock cycle, for example, S0 is processed here. Then the target that you want to exploit is there, but plus 15 other cases that they are completely not considered in your attack. Then it's a high level of noise. But the good point is that the attack may work at the first clock cycle. The data that you want to exploit is also in the second clock cycle, in the third clock cycle, and also in the 16th clock cycle. Every clock cycle is there. Then the information that you have is not only one clock cycle, it's in 16 clock cycles, so 16 different clock cycles. What you can do to again improve the attack, if you have such a kind of shuffling, then you can say, I get again this area of the traces, and this area of the traces, and this area, all the 16, and then sum them up together. Sum. Then you get a single one, which is of course large, but a short one. It's not a long trace anymore. It doesn't cover 16 S boxes, it just covers one S box. Of course, you should keep in mind that these clock cycles that I draw here, they are just imaginary because in the microprocessor, this lookup and also this XOR that you see here, these two, they are not done in one clock cycle. There are multiple clock cycles. That means that each of these guys, this supposedly have multiple clock cycles, not only one clock cycle. And then you do the same for every trace. Again, you do again the same. Means that you take this one and this one and this one. Of course, you align them together in the best way, and you sum them up together, and you get again another trace. For every trace like this, then you have a shorter trace, and then you perform the attack on these summed traces. This is called combing. Why? Because you make a comb, and you sum this point with this point, with this point, with this point, and this point, and this point, and then shift this comb one sample point to the right, and again sum them up at the positions that the tip of the comb shows, and so on. Now it's called combing, but then you perform an attack like this. Why it should work, why it should help you? Because the target that you have, for example, S0, is always there here now, plus noise. Of course, you will still have noise, but it's added here. I mean, you turn the temporal noise to the amplitude noise. One more thing that you can do, which is not dedicated to software, if you're careful enough, you see that the shift rows and subbytes, they do not have any priority to each other. You can first do the shift rows and then a SBox. Then in software, you can easily do it. Means that if you have done the add round key, then afterwards, again, randomly you select whether you want to have the first shift rows and then a SBox or other way around. This doesn't have any effect on the computation results. You may say that, okay, this is the add round key. This is the add round key. If you want to swap between the shift rows and subbytes, then you should either first implement or realize the add round key and then think whether you want to swap shift rows or subbytes, or you apply the shift rows on the key values and plain text as well, before doing the SBox. All of these are just byte-wise operations, the add round key, subbytes, and the shift rows. And as long as you do not mix the bytes, similar to mix column, you can swap them easily, randomly swapped. Good. That was shuffling, and now you know how to overcome this. Of course, I mean, this is a combing, but if the entire operation, like the shift rows and the SBox, are swapped, then the attack becomes a bit harder. Good. A bit about the hardware, how to randomize the clock, or how to add some temporal noise to the implementation if you have a hardware implementation, is simply skipping some clock cycles. You have a hardware implementation and you know that you can model it as a mealy or more machine. It doesn't matter. You have some primary input and you can see it like this. You can have enable for this register. You can have, say, I have enable signal. And if this enable signal is 1, the positive or negative edge of the clock, depending on the implementation, is valid and the register can store some values. But if you disable the register, the circuit actually doesn't do anything. It's exactly something like this. And then this enable signal comes from a PRNG or RNG. Random number generator, or 1 bit. The number of clock cycles that your implementation needs, then of course it will be unpredictable, and it's also variable. It's not constant time. But easily you can apply this. Then what is also important and you should consider, if you do it like this, the power consumption will be like this, and then in this clock cycle, nothing happens. And again, and if you look at the power consumption traces, you might be able to easily detect this. And again, what? Again, here you get some window peaks and the window, and then you avoid this guy by concatenating these peaks or clock cycles, and then afterwards, again, you perform the attack. But if you do this by skipping some clock cycles and then increase the clock frequency, you will not be able to see exactly at which clock cycle the cycle is ignored. But at the same time, if the clock frequency is very high, again, everything is overlapping, and this skipping some clock cycles may not have that much effect. Of course, if you remember, I explained about the clock jitter, means that the duty cycle of the clock is not constant. But of course, you should make sure that the minimum time that you have between two positive edges, this time, this period, is not smaller than the critical path delay. Otherwise, you will have some fault into your implementation, and the result is not necessarily correct. But one question is how to implement this clock jitter in hardware. You have a multiplexer, you have different clock sources into your implementation, and then you randomly select them. But it's not that easy. Yeah? I mean, if you're a hardware designer or you have some experience with hardware, you cannot at any point in time change the clock by this. It means that this is a particular element which is suitable for clock or switching between the clock signals. Otherwise, you will have a glitch into your clock. Because, for example, you have here this is the 2 megahertz, and another one is, for example, 4 megahertz, which is faster, but not necessarily synchron with this guy. For example, first 2 megahertz clock is selected, and then it goes up, and then instantly I select the 4 megahertz clock, then it comes down, and then it goes up again here. And then this period is not necessarily large enough. Then you will have a clock glitch, a very short one, and it's completely uncontrollable, and then it may lead to fault into your system. Then this module is not a simple multiplexer. This should be dedicated to changing the clock, means that it should wait enough to be sure that the both clocks are exactly, for example, at the low, or there is no clock glitch at all, and then at the safe time, it switches from one clock to another clock. Good. Another thing that you can do at the amplitude domain is parallel operation. As I said, you may have another AES. If your target is the AES in hardware, then you have another instance of the AES, which works at the same time with completely random data. Then it adds noise into the amplitude domain or your traces. As I said, you need one more AES instance or some other module which just generates noise. For example, you have an RNG and then some circuits which just consume energy, not necessarily as large as the AES, but something which consumes very much energy. But it has, of course, the area overhead. In the worst case, you have one more AES with random data, and I have to say that even if you have one more AES, which works at the same time with your targeted AES, it's not that much noise. It means that the number of traces that you need to perform the attack will not be doubled. A little bit might be higher because you have just a bit of noise into your implementation. This is what I already explained, noise engines, typically based on the RNG, which they add noise based on some random data into your traces. Good. One more thing, which is also very common, and you can think about it in some particular implementations, is random pre-charging. You learned before about the Hamming distance model when you want to perform the attack on hardware. 2 consecutive values which appear in registers. And then the power model is relevant to the number of bits that they change. if you are able to load a random value into the register before the targeted value is stored in the register, then you may avoid this hanging distance model. But of course, it has some disadvantages, means that it has some overhead into your implementation. Because, for example, you run the AES every clock cycle, and then the registers which are storing something, then every clock cycle you want to first write a random value into the register, and then, for example, a SPOX input comes to the register. What happens every 2 clock cycles you have your AES? Or you make a pipeline implementation. You remember the first session we discussed about unrolled pipeline implementation, means that there are some combinatorial circuit and then register, and then another combinatorial circuit and then register, and so on. You know, for example, each of them is a round of the AES. Now, of course, this is a very large implementation, but it has a very high throughput. And suppose that you first give the plaintext here and then a random data. And then again, another plaintext. This is plaintext 1, plaintext 2, and then another random data. Of course, these random data are not the same. Now, then every 2 clock cycles, you have one valid plaintext or valid encryption. The rest is just random. Then you avoid the Hamming distance model, but it doesn't mean that the attack do not work. I mean, there are some other attacks. I mean, the attacks that do not consider the distance or the values which are changed in the register. For example, you again perform a DPA, you perform a CPA, you perform other attacks that you learn, but based on the value, for example, the SPOX is computing, not based on the transition which happens into the register. This is what I already explained. Then the power consumption will be independent of the Hamming distance of the 2 consecutive values. And as I said, by all of these techniques, by adding the noise either in the amplitude domain or in the temporal domain, you make the attacks hard by increasing the noise, the variance of the noise, and decreasing the SNR. Now we switch to equalization schemes. They are only for the amplitude domain because they don't deal at all with the temporal domain or time domain. They try to either filter something, mean filter the signal that we can measure from the device, or try to make a device in a way that always the same amount of energy or power is consumed. And then, of course, as I explained, it tries to decrease the numerator of the SNR, which is the variance of the signal. And then we have the filtering the power consumption. Now we will see one example. We put a filter between the power supply and the cryptographic primitive to equalize the amount of power consumption. And the other one, the other equalization scheme, which is also set in one of the first slides of the session, we use some dedicated logic styles like dual rail precharge logic, what we will see today, to try or to have the hope that the amount of power consumption for every data which is processed and every operation is exactly the same. Now, filtering. Yeah, this is a just conceptual figure. Inside the chip, you have the AES, and then this is actually a chip. Yeah? And then the filter is there, and what we were measuring, we put a resistor either here at the VDD or at the ground pad, and then we were here seeing the signal or the current which is passing through the circuit. And then the job of this filter is to make the signal that we see flat. First, if we don't have a filter, we will see a power consumption somehow like this. Of course, for every clock cycle. If we assume that this filter works like this, that the amount of current consumption is always constant, that much high, this is not acceptable. Why? Because if you remember, we discussed about the dynamic power consumption of CMOS circuits. If your filter works like this, then the amount of power consumption or the energy consumption is constant, then it doesn't matter if the device works or doesn't work, then a very high amount of current is consumed. You know? If the device is battery operated, the battery will be over very, very early and soon. Or if it's not battery operated, the power consumption, energy consumption of a device is very high. And I have to say that these devices, these filtering things, they are not perfect. Means that you will see something like this. And that might be already enough to perform the attack. Then what they do, and they say, okay, that's too much power. Then let's synchronize this filtering with the clock. Then the clock is also given to the filter. Then the filter works like this. It knows the clock. Then, for example, the power consumption will be something like this. And the idea is to just consume the same amount of current at every clock cycle. Of course, this is the ideal form. It never happens like this. It will be something like this. And so. And again, they consume a lot of energy, but they are not perfect. It means that in theory, they may work well, but there are a lot of parasitic elements and process variation and everything that, again, the deviations that you see at the top of them, if you measure them with a good oscilloscope, then still you can perform that. Even if they work very well, what you have learned, you can have the EM probe at the top of the chip. It doesn't have any effect. Even if they provide any security, they provide security only against power analysis, not the EM. And the other scheme is something like this, which is also based on filtering. What they do, they say, hey, I have some capacitors here. You see C1, C2, C3, which are also inside the chip. And I have some also switches. There are some switches here that the VDD is connected to the capacitors, means that through the VDD we can charge these capacitors. And with the other switches that you see here, two sides of the capacitors can be connected together, means that we waste the energy which is inside the capacitor, means that we can discharge them. With this, we can discharge. With this, we can discharge C2. With this, we can discharge C3. And another one here means that C1 is supplying AES, C2 is supplying AES, or C3 is supplying the AES. Then what we have to do, we should make sure that when we are using C1, means that C1 is fully charged before, through the VD before. Now, it actually is used, means that it supplies the AES. At the same time, we are discharging C2, we are discharging C2, and at the same time, we are charging C3. Then the next clock cycle or next phase, clock cycle, not the clock cycle of the AES, there's another cycle or another clock for this filtering facility. Then C2, which is fully discharged. You see, C2 was completely discharged. Now it will be charged. And C3, which is fully charged, will be used. And that one, which is used before, should be discharged. The idea is that to use one capacitor which is fully charged and then discharge another one which is used before, in a way that when we charge it, the amount of current that we need to charge one capacitor should not be dependent on the data which is processed in the previous clock cycles. Then these capacitors, of course, should be very large and they should be implemented by semiconductor inside the chip. You cannot have real capacitors outside of the chip, otherwise the attacker just cut them. Then they should be with semiconductor inside and they are hard to build. And at the same time, there are a lot of issues. One issue is that these switches are not ideal. They are switches, but they are not mechanical switches. They are also built by transistors. When they are off, there are some current passing through them. For example, consider this phase, phase 1. Then C1 is used, means that this is connected and this is open and this is also open. But this is open, but there is still a little current passing through here. And when you are watching the current passing through the VDD, of course, this is charging C3. Yeah, means that this is also coming through here and charge C3. Yeah, here, charging C3. But at the same time, a little bit of current is passing through this off transistor or off switch. And then again, you will be able to see something. This is one problem. Having very large capacitors inside the chip is another problem. The second problem, as I said, the large capacitors can be solved. Means that inside the chip, you can have it like this. Means that inside the AES, your chip, you can categorize them into or divide them into smaller parts. And say that each tile, which has, let's say, 100 transistors, 100 gates, they have their own capacitors. They have their own C1, C2, C3, and also the charging and discharging facilities, each of them individually. One more thing which is important, the clock of these phases, phase 1, phase 2, and phase 3, should be completely independent of the clock of the AES. No, there shouldn't be any relation between them. Otherwise, you will be able to observe the signals more easily. Because when you switch from phase 1 to phase 2, there are big bumps in the power consumption traces, very large bumps. Because the large capacitors will be charged and discharged. And then if this is synchronized with the clock of the AES, then again, you will be able to easily see what is happening inside the AES. But if they are completely desynchronized, then the attacks become a bit hard. We said all of this, again, if you put the EM probe at the top of the chip, then it will be also easier to perform the attack. But if you have the capacitors like this, a smaller tiles or tiles on this, then if you put the EM probe at a smaller tile, then again, the attacks might be easier to perform compared to power consumption. But because again, everything is local, then you see all the emissions of charging and discharging these small capacitors. Then you will have also noise into your measurements. For the equalization, we need actually a scheme to prevent the glitches. You learned this before. If we have the glitches in your system, then the number of glitches are data dependent, and then every glitch consumes some energy and so on. Now, there are some techniques in VLSI, very large scale integrated systems, to have or to build glitch-free circuits. But of course, they are larger than normal circuits, but some of them can guarantee completely glitch-free property. And some of these properties are not enough to prevent data dependency because they are just for glitch-free, means that guarantee that there is no glitch in your system, but they do not guarantee that the number of toggles into your implementation is constant. Suppose that you build something which is completely glitch-free, but two consecutive values which are stored in a register are the same. Then nothing happens in the circuit. Suppose that one SPOX, this is a SPOX, and this is a register which supplies the SPOX input, and two consecutive values, X and then Y. If we guarantee that this combinational circuit is glitch-free, of course, very good. But if X and Y are the same, there is no toggle at all into the implementation. Then the gain amount of power consumption will be much lower compared to the other cases. Then being completely glitch-free is not enough to avoid data dependency. And then we need a scheme to prevent the glitches and also make sure that the number of toggles is constant, completely independent of the inputs. Means that even if X and Y are the same, then the same amount of toggles should happen inside the combinational circuit. Now, this is the target or the goal, and the solution is dual rail precharge logic or DRP logic. And let's see what they are. First of all, what is a dual rail logic? It's not dual rail precharge logic at the moment. This is just dual rail. It means that every signal or every input-output of a cell is accompanied by its complementary value. If X is the input of an AND gate, X and Y and Z, X bar is also always there, Y bar is also there, and Z is there, Z bar is also there, for every gate and every signal. Now, this is a dual rail logic, not necessarily dual rail precharge. That means that you have X, you have always also X bar into your circuit. You have Z, you always have Z bar also into your circuit. And then what is a dual rail precharge logic? It's exactly similar to this, but it has two phases, precharge and evaluation. It means that every clock cycle has two phases for the circuit. In the precharge phase, you see X and X bar. In the precharge phase, both of them are 0. And in the evaluation phase, only one of them is 1. Evaluation phase, only one of them is 1. Here, X is 1 and X bar is the complementary of X. The next phase is again precharge, both of them are 0. And then evaluation phase, you see X bar is 1 and X stays 0. Again, precharge phase, both of them 0, and the next evaluation phase. It means that there is always one precharge phase between every two evaluation phases. Then this guarantees that you have the same number of toggles into your implementation. Because from precharge to evaluation, only one of them changes. From evaluation to precharge, again, only one of them changes. Look at here again, precharge to evaluation, only this guy changes. From evaluation to precharge, only this guy changes. Only one toggle per signal per evaluation to precharge or precharge to evaluation phase. The idea is to build the gates, AND gate, OR gate, XOR gate, flip-flop, and everything based on this concept. Then the number of toggles, number of glitches, everything will be constant. Doesn't matter which operation is performed by the circuit. One thing that we did not discuss, the idea, the target is to have a constant power consumption. We will see this is good, but there are still some difficulties to achieve this. Okay, then this is clear. Each logical value 0, 1 is presented by two lines, X and X bar, and there are always two phases, precharge and evaluation phase. Both lines go low in the precharge phase, and only one line goes high in the evaluation phase. Something like this. We have seen precharge, evaluation, again precharge, and again evaluation. Yeah, this is another representation. This is what I already explained. There will be no glitches, and the number of toggles will be also constant. One important thing that you should consider, and this is one of the difficulties of these schemes, of these DRP logics, is that the gates are connected together. This is the output of one DRP cell, and this is the input of another DRP cell. Because you build the circuit by connecting the output of one gate to the input of another gate. Of course, some capacitances will be built by this routing, because this will be a route from here to here, another route from here to here in hardware, in the chip. And not only the shape of this route has effect, but also the thickness of the route and the process variation, all of them have an effect. What happens at the end, the capacitance that is there, is inherently built, is not necessarily the same as this capacitance. Then, when this guy changes from 0 to high, this capacitance should be charged. when this guy changes from 0 to high, the other capacitance should be charged. Then there is a small difference between the amount of energy which is required to charge these capacitances. And again, this small thing still is our key. Yeah? I mean, we can again recover a second of the implementation. Although you say, oh, super small, but if you measure enough traces, and you will see this will be propagated. It's not only one signal. This is the entire AES, yeah? Or entire S box. And then for different inputs, there are 200, 300 different capacitances that they are charged. And if you have another input, some other capacitances will be charged. And then if you sum them up together, you will see a very much difference between the amount of power consumption which is required. Then you should try, I mean, there are also some research on that, to route these signals as similar as possible inside your circuit. It means that you build the circuit. I mean, you are not a circuit designer, but there are, for example, some gates here. And the output of this should be routed to this one. And like this. The output of this should be connected to the input of the other one. Of course, you see the length of them might be different. Yeah? Then there are some other tricks to do that, which is called fat wire approach. It says that first route a fat wire, and then when you route it, you've done the routing, then divide this into two parts. Now, because if you don't do it, the placement and router tools will route one of them like this, another one like this. Yeah, not necessarily similar to each other. As I said, I do not expect you to have experience in chip design, but these metal layers, they connect inputs of the one gate to the output of another gate. They go to the metal layers, yeah, not in the semiconductor. Yeah, they have to go to the metal layers, and there are many different layers. When you build a silicon, there are a lot of metal layers at the top that they help you to route these signals. Yeah? Yeah, they may go to different layers, and then they will have a very, very different shape. And if they also go to different layers, then they have also different capacitances. And the idea is to route them very similarly as a fat wire, and then divide the wire into two parts. But this cannot be done by just simple engineering. Yeah? You need very high expertise and experience to be able to do that when you design the chip. Good. Let's see some examples of DRP circuits. Yeah? The first one introduced 2002, which is called Sense Amplifier Base Logic, or SABL. It guarantees constant power consumption for every gate. And one more thing that we will discuss a lot about is actually time of evaluation. It has also independent time of evaluation. What is the time of evaluation? It's like this, yeah, that every gate should generate its valid output completely independent of the value of the inputs. Suppose that you have an AND gate. If the input or one of the input of the AND gate is 0, then you are sure that the output is definitely 0. It doesn't matter what is the other input. But you should not issue the output as 0. Which means that the output of the gate is in the pre-charge phase. It should not go to evaluation phase until all the inputs are in the evaluation phase. If you see one input as evaluated and is 0 and the gate is AND, you directly say, okay, the output is 0, and you go to evaluation phase. And you don't wait for the second input to come. Yeah? Then you already have data-dependent time of evaluation. This should be definitely independent of the data. Means that the time of evaluation should be independent of the data. This issue, as I said, that generating or issuing the output early is also called early propagation issue. Yeah? It means that it propagates the input to the output early. Yeah? It means that it doesn't wait for all inputs to arrive. SABL doesn't have this problem. Its time of evaluation is completely data independent, means that it evaluates when all complementary signals are valid. And one more thing is that all gates actually are connected to the clock to do the pre-charging. To do the pre-charge and evaluation, every gate is also controlled by the clock signal, and unfortunately it needs a full custom design process. One of the things that I explained during the first session in the introduction was semi-custom design process. Means that you synthesize a circuit by logic gates which are available in your library. Means that you don't need to design your library by yourself. You do not need to deal with the transistors. Then you just write the VHDL Verilog and then you synthesize it by the standard logic libraries, and then you build your circuit. Here you cannot do it. You have to deal with the transistors. You will see this overheads, area, and a spit, and it consumes also much more energy. Why it's a full custom design? Because this is one actually AND NAND gate. You see the transistors, PMOS and NMOS transistors, and this is not available in any standard logic cell library. Then this should be first designed by the designer, means that you need to first build a library, transistor level library, and also at the level that you build also the GDS files, means that exactly the layers of the silicon, how you build the transistor and so on. This is very advanced. You cannot just use the standard libraries to build this. Then you need to go through a full custom design process. And you see here the clock is connected to here. When the clock is actually 0, it does the pre-charging. Clock is 0, then this is completely disconnected, and this turns this on, means that this output will be connected to 1, and then this is the inverter, as you know, and this is also inverter, means that this guy will be 1, the output of Q will be 0, the Q bar will be also 0. And then when the clock is 1, then they are bypassed, and then this circuit works and tries to evaluate the A and B. As you see, A bar, B, and B bar, and so on. This is what I already explained. The clock is 0, all signals go to low, and the clock is 1 in the start of the evaluation phase. Then either Q or Q bar goes high when both complementary A and B signals are valid. This is clear. And it has some requirements. The same capacitances for every complementary internal signal. This is the fat wire approaches that I explained, because anyway we are in the full custom design process, then we need to do the routing also by ourselves. This is not something that you can do easily. You need to have experience with chip design, and also not only capacitance, also resistance for every complementary patch should be also the same. And of course, it's not that easy. For that reason, the successor was introduced 2 years afterwards, which is called WDDL, or Wave Dynamic Differential Logic. The benefit is that it works similar to SABL, but it uses only a standard CMOS libraries. Then you don't need to go through the full custom design process. You can do it with the standard libraries. For example, here the AND NAND gate of a WDL is just one AND gate, and here one OR gate. You may think, okay, how this works. You see here A and B are connected to the AND. And here the A bar and B bar are connected to an OR gate, and this is actually a NAND gate. Means that A and B, the output is Q bar, and here if you invert the input, actually you invert also the output, easily, and then you change the gate to the OR gate. This is clear. If you have A, B equals Q bar, means that I want to have Q, then it's something like this, and it will be A bar or B bar. And this is exactly what you see here. A bar and B bar, or, and they make the Q. I mean, of course, in the evaluation phase, this is the way, but how about the pre-charge phase? In the pre-charge phase, A and B and A bar and B bar are all in zero value, zero state. And you see here, the output of this is also zero. And when both of the input is also zero, here the output becomes also zero. Means that if you build the circuit entirely with the WDDL gates and the input of the gate or input of the circuit is completely in the pre-charge phase, every gate automatically will be in the pre-charge phase. Then you don't need to connect the clock into every gate to force it to be in the pre-charge phase. Then it's much simpler than SABL. You can see, it's of course smaller than SABL, but it's less resistant than SABL. The problem of the complementary wires and having the same capacitance for complementary signals is necessary for everything, similar to SABL. I will explain this WDDL flip-flop a bit later. But why is less resistant than SABL? I already explained about complementary capacitances, that it should be actually balanced. There is a problem which is called memory effect. There are some charges stored in the internal nodes of the gates that they are actually data dependent. Here, if you remember how the AND gate is built, they are based on CMOS circuits and CMOS transistors, and there are between two consecutive values, between pre-charge and evaluation phases, there are some internal nodes or internal capacitances inside this but that they stay still charged. They will not be fully discharged inside the gate and also connected to the transistors of the gate. There are some small capacitances that between pre-charge and evaluation phases, they will not be discharged fully, and they have some effect. And the most importantly, the time of evaluation is data dependent. Why? Let's get back to here. This is the AND gate. Suppose that here they are all zero. We are in the pre-charge phase. And then in the evaluation phase, it becomes 1, 1, and then 0, 0. Then it's not a problem. This becomes here in the pre-charge phase, there were 0, 0, and then in the evaluation phase, let's say evaluation phase 1. And then what happens? This will be 0, and this will be 1. But in the evaluation phase 2, of course, there is a pre-charge phase in between. And then I don't write the next pre-charge phase again. But in the second evaluation phase, suppose that then this is 1, this is 0, and A bar will be 0, and B bar will be 1. Look here, A and A bar, and here B and B bar, they are complementary. What happens to the evaluation phase? E2, this should be 0 and this should be 1, which is not a problem. But if there is a delay between the time that the input arrives, suppose that B, which is 0, is faster than A. When B is 0 means that B bar becomes 1 earlier than this guy. Then instantly, when B bar becomes 1, the output Q becomes directly 1. And it doesn't wait for A to be arrived. Then this is called data-dependent time of evaluation, means that it doesn't wait for all A and B to be in the evaluation phase to move from pre-charge to evaluation phase at the output of the gate. Once the input is in the evaluation phase, one of them, the output will be evaluated. Of course, afterwards A becomes 1, 0. It doesn't have any effect on the output. We will see one example with more detail. And this is the most important problem of the WDDL. What you see here, this is in general how the circuit is built. Now in dual rail logic or DRP circuits, dual rail pre-charge logic, here is a combinational circuit which is fully built by the WDDL gates, like here the AND gate. What you should also consider, what I did not explain, what is the inverter in this circuits? I mean, you have X and you have X bar. And then once you want to build the inverter and then the output is Y, the inverter in dual rail logic with DRP logic is actually nothing else than swapping. This guy will be connected here and this guy will be connected here. You just swap the output. And for this reason, you see here is called AND NAND gate WDL. Means that here you just swap Q and Q bar, then you build the AND instead of NAND. How about OR and NOR? You have AND, A, B, C. You want to build OR, let's call it X, Y, and Z. How do you build this AND by the OR by the AND? A, B equals C, right? Then if I invert C, it will be something like this, Oh, this is OR. Is it true? Then that's all. Then if you have a WDDL and NAND, suppose it's AND, then what we have A bar, B bar, and then C bar. What you do to build the AND, to build the WDDL OR, you have the AND, then here is A bar, B bar, and here C bar. Then we need to invert this A and A bar. What was the inverter? Then you do it like this. You do this like this. Do it like this. That's now XOR and XNOR are not that easy. Now, one way to build the XOR of WDL, you want to have A XOR B, then what is it? A B bar or A bar B. Then you need to have AND again, and here OR. Then you need 3 gates to build the XOR. But you know it generally, I mean, you can't build any circuit by only AND an inverter. Because if you have AND and AND, then everything is done. You can build any circuit with that. The combinational circuit is built fully with this WDL gates, and then you need to have the registers. But the registers should also work in the dual rail form and also with the pre-charge phase and evaluation phases. Means that you should have 2 here flip-flops for every cell, every bit, 2 flip-flops, one for the D, another one for D bar, and one more stage to have the evaluation and pre-charge phases. Then 4 flip-flops to save 1 single bit. In 1 clock cycle, 0, 0 is stored here. This is not complementary, means that's the pre-charge phase, both 0, and this is complementary. And the complementary value is at the start of the combinational gates, and then the evaluation phase starts and everything will be evaluated till the end. And what comes here, the complementary signals will be available here at the input of the stage 1. Now, the stage 1 stores the complementary value 0, 0, which was the pre-charge value, will be stored in the stage 2. The 0, 0, or all the registers at stage 2 will be 0, 0, means that they are in the pre-charge phase, and then the pre-charge phase propagates to the combinational circuit till the output becomes also all 0, 0. You know? Then they appear here, and again the register at the stage 1 stores the pre-charge value, and then at stage 2 stores the evaluation value, and this is just repeated. Now, means that every 2 clock cycles you will have one value, means that 1 cycle for the pre-charge phase, 1 cycle for the evaluation. Good. These are what I have explained. And this is also one more example for the early propagation effect or early propagation issue. And these are the gates which are already explained. In some cases, you can have half of the phase of the clock cycle for the evaluation, another half for the pre-charge. But of course, for the registers, both of them should be sensitive to the negative edge and the positive edge of the clock. You know, if you consider this way of implementing. Good. Now, here we suppose that we are in the evaluation phase, and here pre-charge and here pre-charge. We have 3 cases. In one of the cases, A is 1 and B is 0. And here in the second case, both of the inputs are 0, and here both of the inputs are 1. And we suppose that there is no difference between the delay of true and false. You know, that means that with the fat wire approach or something else, we made them completely constant and similar. But there is a delay difference between B and A, because A comes from one gate, B comes from another gate. Anyway, there is this difference between them, because this is something that you can never make constant, you know, because the gates are in different places, and then they should be routed and given to another gate. And now A is slower than B, means that B is faster. And here, look at the output Z. The validity is the correct functionality, of course, is guaranteed. Means that here Z bar or Z false value of the Z is 1 here for this period of the time during the evaluation. And this is the time T of evaluation 1, T of pre-charge 1, and here T evaluation of the true, and T pre-charge of 2, and so on. And this is measured from the time that the clock goes low till the output here becomes valid. And here again from the clock till the output becomes valid, and again here from the clock till the output becomes valid. And also the other one, from the time that the clock goes high and the start of the pre-charge phase till the output goes to the pre-charge phase, the same here and the same here. If you compare them, you see that TE1 and TE2 are the same, but TE3 is different to them. Now, because when both inputs are 1, then it takes longer till the output is evaluated. And TP1 and TP3 are the same, but TP2 is different. It means that the time that the circuit moves from evaluation to pre-charge phase means that this early propagation is not only relevant to evaluation phase, is also relevant to the pre-charge phase. It means that we should avoid early propagation both at the start of the evaluation phase and at the start of the pre-charge phase. Good. I shortly review some other logic styles, and they might be not very relevant and interesting to you, but just as a story that there are many other logic styles designed for this purpose, and we will see that all of them suffer from roughly the same issue. This is a current mode logic instead of the level of the voltage. The current says that the value is 0 or 1. You know, we don't get into the details very much. Of course, it consumes very much energy, but then similar to what I have explained before, yeah? That the amount of current always is passing through the circuit, then the current consumption is very high, then dynamic CML, dynamic current mode logic is introduced, which is also controlled by the clock. Yeah? Means that if you see there is a clock connected to this MCML, the current mode logic circuit. But then similar to SABL, it needs full custom design flow. And there are problems, of course, with the complementary wires. And then you need dedicated placement and routing for the transistor and for complementary signals and also complementary transistors. Now, let's see something else in that area, which is a bit relevant to masking, but we are not dealing with masking completely in this session. It's called randomization in the gate level. Means that each internal signal is masked by a mask bit. What is the mask bit? It means that if you want to represent X, you represent it with xm and m of x in a way that xm is XORed m of x gives you the x. Then suppose that x and y should be the input of the one AND gate. Now xm and here m of x and ym and m of y are the inputs, 4 inputs, and then you have mz. The output of the gate has also a mask of z, and the output of the gate is z of m. Means that instead of having the gate x, y, z, then you have here 4 inputs, which are this one, and also for y, and at the same time you give the m of z, and it gives you then the z of m, and of course together 2 outputs, but this is actually coming from the given input. Then this is super complex, means that instead of one AND gate, then just count. You have here 4 AND gates and 4 XOR gates to just say that or build that this is the AND gate. For every signal in the circuit, you have one mask. But if your circuit has 1,000 signals, then you have 1,000 mask bits. It means that these mask bits should change every clock cycle. Then it's super complex, and it has a very high area and power consumption, and it's not secure. We will see later. This is a concept which is also called hardware masking. We will see why it's not secure later. But then the idea was that, okay, this is too complex. Let's do it in a better or optimized way, in a way that we use only one mask bit. Means that we say m of x equals m of y equals m of z equals m. Means that we define one m for the entire circuit, not only for this gate, for every signal in the circuit, and then we mask every bit with m, which is actually in a way that if m is 0, the circuit works normally as a typical circuit. When m is 1, then every signal is inverted. When you XOR one value with 1, means that it is inverted. Means that x bar, if you XOR with 1, then you invert this. When m is 1, every signal in the circuit is inverted. And based on this concept, some circuits have been built, random switching logic, and then dual rail random switching logic, and then mass dual rail pre-charge logic, which is called MDPL, and another one, improved version, and so on. I do not want to spend very much time on this DRSL, random switching logic, and so on, but just as a reference, you see here that the circuit or the signal is not complementary. Means that x1, x2, the invert of them are not there. x1 and x2 are the input of the gate. And this is actually one NAND or NOR RSL gate. And then there is R, random value. As I said, we don't want to get into the details, but this works like this, that if R is 0, the circuit works normally. If R is 1, it is assumed that the input is inverted and output is also inverted. What is the enable signal? The enable signal actually moves the circuit from pre-charge phase to the evaluation phase. It means that it's a pre-charge circuit, but it's not a dual rail circuit. The number of targets is actually data dependent, and it doesn't provide security as we want. But the bad thing about the circuit is that if you have a circuit like this, I mean, there are some gates. And the input of them, for example, are connected to here, and this one to here, and this one to here. And for example, another primary input, I'm coming to here, and here, and here, and so on. No, it doesn't matter. The thing is, these gates, which are in the middle, should not evaluate until the inputs are completely evaluated. And these gates should not be evaluated until all inputs are evaluated. Who should actually control this? The gates which are in this depth, for example, they have enable 1. And the gates at this depth, they have enable 2. And these gates have enable 3. Then, first, all of them should be 0. No? EN1, EN2, EN3, for example, all of them should be 0. And then enable 1 comes 1. And then after some time, this should be 1. And another time, this should be 1. Then you need a controller. And then when you want to turn it off, again, this one should be off first. And then this one should be off first. And then this one should be off. Then this is not easy to achieve. Then you need another circuit to control this. Then DRSL, which is a dual rail random switching logic, is introduced. And these gates that you see here, RSL NAND gates, they are the one that we have seen in the previous slide. And one module is added here, which controls the enable signal. This is nothing else than here some OR gates and AND gate. It checks if all inputs are in the evaluation phase. It means that all of them are complementary. If they are all complementary, then the enable of these gates should be active. How do you check if they are complementary? It means that you see here A and A bar. If one of them is 1, means that you are in the evaluation phase. Because anyway, only one of them will be 1. And in the pre-charge phase, both of them are 0. This should be 1, which means that A or A bar is 1. Here, this should be also 1, means that B or B bar is 1. The same here, M and M bar, the mask value. One of them should be 1. Then if all of them are in the evaluation phase, then the output of this NAND gate is 0, means that they will be enabled and they can work. This is what I already explained. It prevents early propagation. You see, it waits till all inputs are in the evaluation phase, and then it commands the gates to be evaluated. But it leads to information leakage in the pre-charge phase. It means that once one of the inputs goes to the pre-charge phase, instantly the output goes also to the pre-charge phase. This should be also not like this. Now the next one is the MDPL, which is very similar to that one that we have seen, masked dual rail pre-charge logic. It can be seen as a masked version of the WDDL and can be also implemented with standard CMOS library. The concept actually is like this. It has a majority gate, and the majority is clear, right? Majority gate means that A, B, or, I mean, this is the OR gate, not the XOR gate, or AC or BC. Means that at least 2 inputs should be 1, then the output is 1, then the majority. If 2 of them are 0, then definitely output is 0. Functionality is based on a majority gate, and you see here A and A bar and B bar and B and M the same. Again, if M is 0 and the circuit is working normally, if M is 1, every signal is inverted. Because we have dual rail logic, then it means that A and A bar are swapped. What is the idea of this? You remember the problem of WDDL, that we need a fat wire approach and to control the placement and routing. Now the idea is to randomly change M, then you don't need to care about the placement and routing between the two signals. This is the idea. But MDPL has a problem, early propagation effect, similar to WDDL. Means that it solves the problem of the fat wire approach or having a balanced routing between complementary signals, but it doesn't solve the problem of the early propagation effect. And it actually has been built in ASIC, because you should keep in your mind that most of these designs, logical styles, have been designed first, of course, and checked in simulation domain using a SPI simulation, if you remember I explained before, in transistor level simulation. But a few of them have been really built in practice and checked, and one of them was the MDPL. It was built on the circuit prototype, and a very high amount of leakage is also seen in practice. For that reason, there was a successor, IMDPL, which is the improved version of the MDPL. And it's very similar to MDPL, but it avoids the early propagation effect. How? These are the two majority gates that you have seen, and this large circuit is added in front of every gate. What it does, it actually checks if all inputs are in the evaluation phase to say, hey, evaluate. And it also checks when all signals are back into the pre-charge phase to say, go to the pre-charge phase. Means that it avoids the early propagation in evaluation phase and also in the pre-charge phase. And do you remember, from the first year of your study in digital technique, logic circuit design, what is this? Cross-coupled NOR gate. It's a latch. Means that it stores the value, because some signals go to the pre-charge phase, and it wants to keep them till everything is in the pre-charge phase. Then it has here one circuit similar to what you have seen for DRSL. This was a simple thing. All of them here are in the evaluation phase, and this will be 0. And this commands actually these latches to save or not save. And they are the input of the majority gate. And this actually is much better, but it has a very high overhead. You can imagine that circuit is just one AND gate. This is also prototype, and practical investigations also showed very much leakage decreased. But these schemes have another problem. You see here, as I said, M and M bar are what? They are the same for the entire circuit. And you can see M and M bar are connected to every gate. And there is a very large capacitance for M and M bar circuit. And then what happens when both of them are in the pre-charge phase, M and M bar. And then one of them moves to evaluation phase, having 1, means that either M or M bar will be 1. But because the capacitances are different, this change from 0 to 1 for M is different to M bar, means that the amount of power consumption will be different. Then for every clock cycle, you will be able to recover the value of the M. Means that this is the power consumption. And then, for example, you look at this part for all of them, for all of the traces that you have at this point in time. And then you look at the distribution, you will see something like this. And then you say, here M equals 0, here M equals 1. Or other way around, doesn't matter. Then you categorize them. You say, consider only those traces that they have the same M and or the same M. Even perform the attack on these traces or on these traces for this cycle. For the next clock cycle, you have to do the same, and categorize them, because M is changing every clock cycle differently. Now, there are some other logical styles, asynchronous logic, some charge recovery logic. They are based on some other concept to use the energy which is stored in the capacitors and reuse them and so on. Most of them need full custom design process because they change the structure of the AND gate and fundamental gates and so on. And they have very high overhead and energy consumption and so on. What we should consider, some of the logic styles only make the circuit actually more complex without adding meaningful resistance against attack. One reason is that most of them are evaluated in simulation domain because there are many other parameters that become apparent in practice that we are not able to easily cover them in simulation domain. For example, these are SPICE simulations. Of course, there are schemes to cover the process variations, but the process variation is not considered for the simulations and evaluations of these schemes. And some of them make the attacks harder, not all of them, but the area and the time and energy overhead are very high, and they mostly prevent the designer to take them. Some of you will work later in some companies, and then somebody will ask you, okay, you cannot easily convince the customer to buy one IP from you, which is, let's say, 10 times larger and it has 10 times higher power consumption, but it adds a bit of security. And the research in this area were not as active as before because we learned, or the community learned, that they can make the attacks harder at the end in the best way, but with very much of overhead. One more thing is that the simulation tools that we have are not really appropriate to evaluate these logic styles, or were not appropriate. At the moment, there are better things to consider and better evaluate these schemes when they are combined with masking schemes. The masking schemes is something that we will see later from the next session. And one part is hardware masking, and then there are some benefits of using this dual rail logic schemes or dual rail pre-charged logic schemes when they are combined with masking, and then they can mitigate some issues that we have with masking. We will see later. There are some references, and yeah, if you want to read, there are many more things to read.
Were any of those methods implemented in mainstream processors?
I think some of them were taken by some companies. I mean, I don't want to name the company. No, at the moment, I'm not aware of any of these schemes to be used. But in combination with masking, yes. In combination with masking, there is a company which invented a particular combination between dual rail pre-charge logic and a masking scheme. Because masking scheme that we will see later, they add a lot of latency to the system with respect to the clock cycle. It means that if you have an unprotected implementation, for example, AES, in 10 clock cycles, you can have the AES encryption if you want to have implementation around based. But if you implement masking or add masking to that, then the number of clock cycles will be multiplied by 4, for example. Now, then instead of 10 clock cycles, they need 40 clock cycles. Then the combination of that provably secure masking scheme, with some logic styles that we will see later, this will allow you to actually have the provable security with respect to the masking, but keep the number of clock cycles again to 10. These are some benefits. And this achievement could not probably be achieved without all the research which have been done in the dual rail pre-charge logic.